Good morning. First of all, Happy New Year. This is indeed a thermodynamics video, but as usual, I'd like to begin this video with a very quick discussion. Quick discussion and update. First and foremost, as those 10 people that watch these videos randomly, or not randomly, I'm not certain. As you know, I've not been uploading, well, at all, for the last at least 2, almost 3 weeks. And the reason being is because, for the same reason that I gave him the last set of videos that I put out, just time. But now, I've set myself up to be able to really put on a very more realistic schedule. Not very, but more realistic schedule. And the schedule for these videos, I will upload another video to talk about the schedule and things. But the schedule will be on Tuesdays and Thursdays. You will get thermodynamics and electrodynamics videos. So Tuesdays would be thermodynamics videos, but because it's Thursday, I'm going to put out both the thermo and the electrodynamics video for today. And then on Saturdays, we'll do plasma physics videos or reviews of research. And reviews of research is going to be something new that I've wanted to start it since the very beginning of me putting out these videos in the first place. Just hadn't given myself. Let's not say, and that's the other part of the discussion. But anyway, I haven't given myself the adequate time to really put that to fruition. The other part of this discussion is something about I want to give. I'll probably also make a separate video about this, so there'll likely be 4 videos out today. And the 4th video will talk about the importance of this realistic time. Giving yourself adequate time, especially when you're studying something as complicated and something as beautiful and something as very time-consuming as physics and mathematics. The practice, the problems, the reading, it takes a lot of time to do, and it takes a lot of patience. But more importantly, it takes dedication. And it takes discipline. The time that you put into studying math and physics, especially for physicists and mathematicians, this is your training time. Actually, this isn't just your training time. This is part of the necessary steps for your future. And this discussion isn't just good for mathematicians and physicists. This is really good for everyone. Because there's this unrealistic idea that you put in a little bit of time and you get a lot of effort. And unless you're a genius, which I am not, gifted, maybe, but I'm not by no means a genius. You are not going to put in a little bit of effort and get a lot out of it. So to better do these videos, I have to look at it I have to come at this from a different perspective and give the best quality of videos that I possibly can. And I really want to do that for those people especially those people interested in math and physics. But again, that's going to be another video. This is a thermodynamics video. And I'm testing out a different format for the remainder of all the videos and content that I'm putting out. This is my good morning, hello world tea in my courage mug. I love this mug. Anyway, This new format is going to be sort of like, well, not sort of, more of a tutorial than just a problem solving session. Now, I looked at the other videos and I took into consideration a lot of the other insight that I received from folks that watch my videos and say, okay, yeah, you're doing the problems, but I didn't really learn anything from it. You're right, you didn't. You probably didn't, because unless you were taking the course or you had that exact same book, you didn't really get much out of it. So what I want to do is I want to actually explain the concepts somewhat. This isn't going to be a lecture per se. There's going to be sort of lecture-like elements where I give explanations, but for the sake of time, since I already more or less have 30 to 50-minute videos, I'm going to give an overview of the chapter information and then jump into the problems. And while people will be like, duh, why didn't you do that before? Well, I didn't do that before because the videos before were more narcissistic, and I believe that's how they would come across, is that they're more narcissistic than meaning to be helpful. And these videos aren't meant to be narcissistic. They're not meant to be misunderstood as just me showing off the fact that I'm smart and that I can do problems. No, they're meant to help people. So let's do that. The end of chapter 1 of thermodynamics more or less talked about concepts that aren't exactly very helpful, like the enthalpy, not the entropy. That sort of idea isn't really important for thermodynamics. It may be later, and when it comes across as being absolutely essential to understand the concept, then I'll go through and I'll explain it. But a lot of the concepts towards the end of chapter 1 of Schroeder's thermodynamics book aren't really, they're not really helpful. So instead, I plan on just jumping to chapter 2, where we actually get started and start talking about thermodynamics. First of all, the music in the background today, other than my neighbors who are very active people, question mark, big question mark over my head, is Debussy's, the best of Debussy of YouTube. Specifically, right now that's playing is Clair de Lune. I love Debussy. And please no filthy Frank references. Alright, so in chapter 2, like I said, we're getting started to talk about what thermodynamics is and thermodynamics like processes and those sorts of things. Specifically, we talk about, well, in the beginning anyway, we talk about counting and what it means to count large numbers or large quantities of objects. In a lot of instances, it's energy. We'll see in the beginning chapters, we'll be counting units of energy, counting units of, not units, but oscillators in the context of Einstein's solids. Thank you, Debussy. Counting how energy is distributed among Einstein's solids, and looking at the various ways that you can go about, thinking about temperature and that conversion of energy and temperature. And specifically, a lot of that is, it's a lot of information and a lot of generality there. But we're specifically, at least in the first couple sections that I'll be introducing, looking at something called the multiplicity. And if you've read Schroeder, or even if you haven't read Schroeder, the definition of multiplicity is, I'll write this because this is going to be pretty important. And this is my definition. And actually, this will be more helpful for mathematically inclined people than it will be for non-mathematically inclined people. Because the multiplicity is, I have to use money. because it's a multiplicity. So is the number of microstates in a given macrostate. And you see why I said that it's not as, it's not as helpful. Wow, you can't even really see that. But anyway, it's not going to be as helpful for regular people or for physicists than it's going to be for mathematicians. The number of given microstates, the number of microstates in a given macrostate. What does that mean? Well, then you have to look at what's the definition of a microstate and what's the definition of a macrostate. And, well, the best way of doing that is the best way of understanding that is through example. So let's do that. And the easiest manner of going about, looking at the multiplicity, of a system, because you don't just look at the multiplicity of something, you look at the multiplicity of a system specifically. And a lot of times those systems have a large, or even can sometimes even have a finite number of combinations of things. And this is those combinations, and those number of combinations are your microstates. Yeah. Your microstates are the number states, but really they're the states specifically. So where you have this area, let's call it omega, because that's my favorite Greek letter. You have this area omega, you have these little areas, and sometimes they may overlap, they may not overlap. Actually, they have to overlap in order to encompass the area omega. And some of them have to overlap to encompass the entire area of omega. That's just set theory. You have these little areas. Show that some of them overlap. You have these very little areas, and you call them, alpha. These are your microstates. And the number, actually really the number of these states, or the entirety of these states, is your macrostate, and that is big omega. Now that's not what I had in my notes, that is what came up off the fly. But why is this going to be important for thermodynamics? Well, I'll show you. I'm going to show you. Schroeder introduces us to one of the most simpler ways of counting micro and macro states, and that is through the two-state problems. And the two-state problems usually are best, the best example of two-state systems. The best way of understanding them are really through coin tosses, because what's better, than for a two-state system than something that is up or down, heads or tails, an electron spin up or down. The difficulty of electrons, though, for microstates, I'll explain later, is that electrons can also be in a state, can also be connected to are limited by their spin in terms of atoms, by the Pauling exclusion principle, and entanglement. So again, I'm jumping the gun a little bit, and I do that. I jump the gun. But this at least shows you that, you know, I'm thinking about shit before I actually write these notes. So Schroeder gives us this basic example of you have, because we're looking at counting, we're looking at macro states and micro states and macro states. Gives us this example that you have 3 coins. You have a penny, you got a nickel, and you got a quarter. Schroeder uses a dime, but I like quarters. Get over it. So you have a penny, a nickel, and a dime. And the question is, you know, how many distinct ways can we get, or can we count the combinations of their coin flips? Now that's a really convoluted way of saying it. And actually, I think that he says it better, and I'm gonna give his way of asking this problem. So the statement is, this is from Schroeder. Suppose I flip 3 coins, a penny, a nickel, and a quarter. How many possible outcomes are there? And I add the word distinct because that's going to be very important, because for this reason. You have, for the penny, of course, you either have heads or tails, nickel heads or tails, and quarter heads or tails. So how many distinct outcomes are there for these three coins? Or for these 6 possibilities of coins? Well, let's list them. We've got time. You can have heads in the penny, so there's penny, nickel, one. So heads for the penny, heads for the nickel, heads for the quarter. You're lucky, 777. Lucky. All right, so you can have heads all 3, or you can have tails all 3. Okay, that's 2. Let's say that the heads are held fixed for the penny and the nickel. So heads, tails. Let's shift the T over to the right. Heads, tails, heads. Shift the T over to the left. Tails, heads. So let's analyze what we have so far. So we have, at this point, we have 5 different outcomes for our experiment. You have 1, which is all 3 heads, 1, all 3 tails, and 3 with just 1 tail, or 2 heads. Okay. Now let's look at this from, well, let's finish. Because we're not done. We can have the combination where we only have 1 head. Let's do that. Head on the left, tails. Okay. Let's shift both over to the left. Tails, heads. Shift both over to the left again. Okay. Do we have any more? Do we have any more for this? I don't think so. I think that's it. Yes, that's it. So let's look at it from the head's perspective, because I find it, for me anyway, just for me, either way doesn't make any difference. You can look at it from, you have 2 tails or you have 1 head. It doesn't make any difference, but let's say 1 head. 2 heads. 0 heads. 3 heads. Like my shoulders. Anyway, so these are your outcomes. In general, these are the possibilities, of the total possibilities that you can have for this experiment, for counting the number of outcomes for the 3 coins, or the results of the 3 coins. Which is pretty cool. And from the perspective of micro and macro states, well, you have you can have 1, 2, 3, 4 different macro states, or one whole macro state, the micro state of the experiment, the macro states of the 1 head, 2 heads, 0 heads, 3 heads, so 4 macro states. But you have 1, 2, 3, 4, 5, 6, 7, 8 microstates. You have 3 microstates in the 1 head, 3 microstates in the 2 heads, 1 microstates in the 0 heads, and 1 microstates in the 3 heads. The next and most logical step, to getting into this is, what is the probability of getting a 1 head macro state? And that's where the multiplicity comes in. That's where the multiplicity comes in. And again, I'm going to go to Schroeder, even though I have in my notes, I think that he says it better. You say, remember what we said about what the multiplicity was. The multiplicity was the number of microstates in a given macro state. So we're going to define the multiplicity by a function excuse me while I erase. That would be very helpful. Well, the beauty about bringing multiple erasers, even if you lose one, is that you got plenty more. We're going to define the multiplicity by a function, again, omega, because it's my favorite Greek letter. Don't ask me why. I know the answer, but I won't tell you. We're going to define the multiplicity by this function, omega, and n by the number. Whoops, didn't let it dry. For those Jurassic Park fans, I'm giving up my age at every single turn today, ain't I? Alright, so this is going to be the multiplicity. That's your multiplicity. This is our multiplicity. And, I say it's a function, but whatever. Just relax that part of your brain for a second. It's an object. And, what is the probability that we get one of these macro states from the entirety macro state, or from the system as a whole? And say we define that probability as That's what we define that probability as. The probability of that particular question. The probability of getting one of these macro states from the system. And so let's look at it. So okay, well, what's the probability of getting one head? Well, probability of getting one head, or the macro state, or the multiplicity of getting one head, is 1, 2, 3. And the multiplicity of all of them are 1, 2, 3, 4, 5, 6, 7, 8. So the probability of getting one head is 3/8. So far, so easy, okay? Now look at the multiplicity of getting two heads. Well, it's the same. 1, 2, 3, all is 8. So 3/8. What's the multiplicity of getting 0 heads? Well, you have 1. The multiplicity of 0 heads is 1. So this would go . And then you get 1/8. Okay. Well, so far that's pretty easy. Now, when we start talking about things like, not a penny, nickel, or dime, but penny 1 through penny 1,000, that's when we start getting much bigger and more complicated, or we have to look at much more complicated matters of counting. Because right now, I mean, we can count the combinations for 3 coins. It's heads or tails for 3 coins. And, we don't have to look at anything super complicated like, say that, the heads of the penny determine the head. And the reason why we can look at it, and it's, simple like this, because the heads of the penny doesn't like hold back the heads of the nickel or hold back the heads of the quarter or, the coin flip of the quarter. These are independent systems. These are independent objects, where the coin toss or the action of, or the measurement of experiment on one doesn't affect the measurement experiment of another. And that's what I was talking about, things in terms of like objects being entangled. Those are quantum mechanical effects on electrons and subatomic particles that we don't have to worry about. But even for things that are non-entangled, like quarters and coins, if we start looking at large numbers of them, it starts getting weird. And specifically, if we start looking at, like I said, large numbers of things, this is where I start to really use my notes, because I don't think that Schroeder introduces this concept very well. We can erase. This was my original eraser. We can erase things. And actually, what I'm using is sea breeze. So, well, alcohol specifically. So it should dry out fairly quickly. This is why I'm talking. I'm gonna let it dry out. Specifically, when we start dealing with large quantities of say, coins in this example, since we are talking about the two-state system, start dealing with large numbers of these things, we're going to have to use a little bit more sophisticated machinery. And the sophisticated machinery is called Combinatorics. This is something a lot of people have already been introduced to. You've probably seen it in like middle school math, maybe not middle school math, maybe high school math. Briefly it was discussed in, maybe some, if you're not abstract. Yes, you would have seen it in abstract algebra, but and like your pre-algebra courses and things like that. If you've been, most people are taking pre-algebra, and then by the time that you're in college and watching my videos, you've definitely seen it at least once. But let's do this, and let's just hit it, because there's no good way of explaining why you need this. So I think the best way of doing it is just to hit it, and I'm going to hit it by my notes. And the topic that we're going to be discussing are number of distinct pairs. And the important word in this concept are distinct. The operative word is distinct pairs. Because we can get pairs where, you have, say simply you have three letters. You have A, B, and C. And we want to look at the number of ways that we can organize A, B, and C. In general. Let's not even worry about distinct yet, but just the number of ways that we can organize A, B, and C. We could say B, C, A. Of course, we have A, B, C. We could have A, C, B. You could have C, A, B. Back cap. A, B, C. A, C, B. Okay, we got that. B, C, A. B, A, C. C up front, CBA. So how many ways? 1, 2, 3, 4, 5, 6. Is that correct? Well, yes, it is correct. This is the number of distinct pairs that we have here. This is the number of ways that we can recombine this structure here out of these three letters. And what is this number? This number is actually not 6 factorial. Whoops, 3 factorial, which is, by definition, 3 times 2 times 1. So you multiply out the integer values in this case. Multiply out the integer values all the way up to 1. And these are your number of ways of making this combination. Now, what about number of distinct ways of this combination where you don't have any copies? Well, A, B, and C are easy because this is a very easy way of bringing this topic up, is because you can't confuse A with B or B with C. Why? Because they look different. You can't confuse it. These are obviously independent objects that you're combining. But let's get rid of B and let's put A and then A, C. How many different ways can we combine this? Well, of course we have these. We have all 6 of these. But then let's switch A's around, and we can do that an infinite number of times. But we also have to then divide by the number of spots that we have. And this is where this concept is going to be. This is where this concept is going to be pretty important. Because say we don't have 3 or a finite number of objects. Say we have n number of objects, and those n objects. Yes, I have a very ugly erasing hand. I'm sorry. I can't help it. I erase ugly. So we have n objects. So we can pick out of, not from 3, but capital N different objects. And we just want to randomly pick from these n different objects, and we want to know how many different combinations of two distinct pairs that we can make out of n different objects. Well, we pick from n different objects, so we have the first spot, and we have n possible choices. But then in the bag, say there's a grab bag, we have n minus 1 possible choices. We pick this is our second pair, and we have n minus 1 possible choices next. So you have n times n minus 1 possible results for those two choices out of these n different objects. But say we picked the n minus 1 object first, as opposed to the nth object, or the nth, and then we picked the n minus 2 object. Well, how do we overcome this? Well, instead of worrying about specifically the object's name that the numbered objects that we place, we divide by 2 so that the order doesn't matter and we have a distinct pair. Okay? Yes, this concept seems, pretty weird, and let me zoom in a little bit, because this is the ghetto zoom, because I feel like camera's a bit off, and I know that it's been this way the entire video, but whatever. We're gonna notice that something's wrong and then just fix it, right? So the pattern is, say we have to pick from 3 different objects now. We have to pick now one more object before we divide. We have to multiply it by n minus 2. And then divide by 3. Because we have 3 different possibilities for the order of these three objects. And so that the order doesn't matter, when we get distinct triplets, we get rid of those copies. And the example that I use, or the example that I like to use, that helps me deal with, combinatorics and, this whole idea of distinct pairs is, species of birds. Yes, I like birds. Actually, I like birds and I like insects. My favorite insect is the fly, and I know that I probably shouldn't be talking about this like sort of like an eHarmony commercial. But my favorite insect is the fly. And anyway, I love birds, especially love ravens, love cardinals. Very beautiful birds. And I realized how much I knew about birds by my last job. Yeah. Pretty bird-brained human being right here. So let's give a big number to n. Let's give capital N a number. And I'm going to take the species of birds, the number of species of birds, and there are 10,000 species of birds. Actually, there are 9,989 different species of birds. So we're going to say that there are 10,000 different species of birds, give or take the number of species that scientists or ornithologists, something, have missed since antiquity. And we want to put 3 different species of birds, pick out of the 10,000s 3, and put them in a very special bird cage. Oh, I'm sorry, birdies. First of all, this cage is going to be, I know somebody's going to be like, is that a watermelon? Shut up. Okay. That's an ugly watermelon right there. It's a bird cage. I'm going to give them 3 special bird cages. First of all, bird cages are so inhumane, but in the same breath, birds just shit all over the place. So, we have 3 very special bird cages, and we want to take, we take 3 of our 10,000 different species of birds and put them each in a bird cage. So, what's the procedure? Well, let's do it all over again. We have, we'll say 10,000 equals n. We'll take 1 out of the nth n possible different birds and put it here. And we'll take n minus 1, 1 of the n minus 1 remaining birds, and put them there. Different number of birds left, different number of the birds remaining, n minus 1, and put it in this cage. Then we'll take n minus 2. And so that we're only looking at the distinct triplets of birds, we divide by 3. So we have n times n minus 1 times n minus 2 over 3 possibilities. And we can extend this to an nth number of times. And if we do this an nth number of times, well, if we have an n number of bird cages and we want an n number of distinct nth pairs, then what do we have? We have n times n minus 1 times n minus 2 times n minus 3, so on and so forth, down to 1 bird left, and then we divide by n. Well, what is this? Well, I've already introduced this to you. This is called n factorial. And actually, when you divide by n, actually, bit of an error here. I think I made a bit of a boo-boo. Did you see? We're not just dividing by 3. We're actually dividing by 3 factorial. And the reason why we're dividing by 3 factorial is because, yeah, I made a mistake. And I apologize for this one. The mistake I made was, we're not just dividing by 3. In my mind, I was saying that I was cutting out the number of different combinations that you can make out of these 3 different choices. Well, we've already established that you can make 6 different combinations, right? If you look at the combinations of A, B, and C, they're different. These are different. These are distinct. We don't care about, picking a cardinal, blue jay, Oreo. We only, or Oreo, cardinal, blue jay. We don't, okay. This is the important part. This is the important part of the discussion. And actually the part that I missed. And I'm going to make a separate video to do the problems. But we don't care about, say we pick cardinal for the first bird. Then we pick an Oreo. And then we pick a blue jay. We don't care if we pick a blue jay first, then a cardinal, then an Oreo. What difference does it make? You still have a cardinal, an Oreo, and a blue jay. We're only looking at distinct pairs or triplets in this case. So we cut out all the bullshit and we divide by 6. And that is the number of different combinations that you have. You're dividing not by n, but by n factorial. This is n factorial already. So really, you only have one possible combination if you pick out every one distinct combination. If you pick out all of the 10,000 birds and you put them in a cage. If you just want to look at the different combinations, you have n factorial combinations. You're not dividing by anything because you don't care as to whether or not your combinations are distinct or not. You're just looking at the number of combinations that you could make out of all those birds. But if you're worried about the distinct pairs, you have to divide out by the number of different combinations of cardinals, Orioles, and Blue Jays that you have. Okay, that's it. For now, that's it. I'm going to put out another video in just a few minutes to do the problems. Thank you. Thank you for watching. And I realize that everything's a bit messy right now, but that's because, as you can see, I look at my recording while I'm talking to you guys. And so that I can, I'm trying to make or find the best way of organizing this and, really getting my feel for, doing these little tutorials beforehand. But this is going to be fun. Let me know if you like this new format. I will see you in a few minutes with the problems from the problems or the first few problems of the sections of chapter 2. Till then, bye-bye. Stay sexy, folks.